Earthquakes are the shaking of Earth's crust caused by a release of energy. Imagine you have a stick, no strain on it, and then as you pull your hands in different directions, the strain builds up, builds up, builds up until snap. The stick breaks and they reverberate back into place, so they're no longer bent, and it releases a huge amount of energy. That's precisely what's going on in the Earth's crust. The strain builds up in opposite directions. In this case, this is a shearing stress. One, they are going sliding against each other, if you will, such as at a transform boundary, until snap, it goes back into place. There's a certain location where the original snap began, and then waves of energy radiate from that point. This is the diagram in your notes. That point in the center where the crack first began is called the focus, and that is the actual center, the actual source of the earthquake. The focus, not the epicenter. The focus is the actual place where the earthquake occurred. The epicenter is directly above the focus along the Earth's surface. So we talk about the epicenter more frequently than the focus because we live on Earth's surface. We don't live 4 kilometers deep where the actual earthquake happened. We live at the surface, so we talk about the epicenter. But the actual earthquake happens at the focus inside the Earth. The crack that forms is called the fault. All right. And you see here where the fault may appear at the surface. And then there's energy that radiates in all directions, and these are called waves. And they are waves of energy, much like when you drop a pebble into a pond and you see the radiating ripples of energy. Now there are different types of waves. The first is called the P wave. It's a compressional wave. It's kind of like, as you see in this image, if you imagine a slinky, and it's a push wave. It's pushed together and then stretched apart. And this is a very fast moving wave, and it radiates throughout the rock in all directions, up, down, left, right, everywhere. And it can travel through solids, liquids, and gases. And this, since it's so fast moving, arrives first at any particular location. These are some examples of motions we see at Earth's surface due to P waves. Here we had an elevated highway in Shichi, Japan, and you can see how, if you imagine it being pushed together and then pulled apart, you can imagine how this section here, after being compressed and then stretched, would thus fall off of its supports. It's contracting and expanding also, and it can cause building damage as well. Now what's kind of neat about these P waves is that since they travel through solids, they travel through the rock, they also travel through liquids, so like this lake, a pond, and they also can travel through the air. So if you are in an airplane directly above an earthquake when it happens, the P wave would actually radiate up to hit you in the airplane as well. Next we have the S wave. It's also called the shear wave. I like the name of it, the S wave, because it stands for S for solids. It's the second to arrive, and since it's an up and down, right angles to the direction it moves, it's almost like an S shape. So it's a very appropriate name for this type of wave. It's an up-down movement. But since this has less energy and travels slower, it only can travel through solids, not liquids or gases, so you would not feel it in the air, and you would not feel it in the middle of a lake. But this is what it does to the ground. It's almost like someone here with this brick road took the brick and shook it up in the air, much like you were shaking a sheet. Lift it up real fast and put it down real fast, laying out a sheet on your bed. And it causes some interesting movements to the buildings. Now these are just the two most important types of waves. We also can get surface waves that do more of the surface damage, and those are called Love and Raleigh waves, but we're not going to get as much into those. Most studies of seismology, the study of earthquakes, deal with P and S waves. These are those surface waves I told you about. The Love wave goes side to side, named for a Dr. Love, a scientist Love, and the Raleigh wave, which is more of a circular pattern, much like the waves in the ocean. All right, a seismograph is the instrument we use for measuring earthquakes. In the most basic level, you have the rock, and attached firmly to the bedrock is a rotating drum with paper on it. And since it moves with the rock, it will move up and down just when the rock moves. Over here, we have suspended from a support, a spring, um, a weight. Now, since this is suspended, no matter how much the rock moves, the weight will remain in one point. So as the rock moves, it moves the paper up and down, and then the pen suspended on this weight doesn't move. So we get a recording called a seismogram of the Earth's movement. It'd be going straight and then stoop, poop, up and down a little bit when the P waves hit, and then a larger, greater bouncing movement when the S wave hits. Notice the P wave arrives first, it's also called the primary wave, and the S wave arrives second, also called the secondary wave. The secondary wave creates more vertical movement because the P wave is just a side-to-side movement, whereas the S wave is an up and down movement. Notice at the bottom we have time markers. This is saying 10, 12, 10, which means 10 hours, 12 minutes, and 10 seconds. The S wave arrives at 10 hours, 12 minutes, and 40 seconds. So what's the time difference between the P and S wave? Well, the The hours and the minutes are the same. The difference is the seconds. 40 minus 10, that is 30-second difference. And that's going to be useful later. So a seismograph is what we use to detect waves. We need 3 of them to triangulate the location of an earthquake. Before we get into triangulation, let's briefly explain how we measure earthquakes. We use something called a Mercalli intensity scale, which measures the effects of an earthquake on humans and the damage it causes. The closer you are to the epicenter, the more the damage. And also, if you're on loose soil, you get more damage. The magnitude scale, the Richter, measures the strength of an earthquake in terms of the energy it releases. Here's the earthquake. 0 to 1.9 only detected by a seismograph, all the way up to a 9 and over, which is virtually total destruction. The earthquake we experienced here in Virginia in 2011, August, was a 5.8, which was in this range. Furniture can move, chunks of plaster may fall from the walls when you are right at the location. As far away as we did actually feel it, and small objects are able to fall. This is the magnitude scale. Each time you go up, you're actually multiplying by 10. So a 2 is 10 times more than a 1. A 3 is 100 times worse than a 1. 4 is 1,000, 10,000, 100,000, a million, 10 million, and so forth, all the way up. In 1960 Chile, there was an earthquake that was about a 9.6 on the magnitude scale. And that is more powerful than the Hiroshima bomb. This was the atomic bomb dropped on Hiroshima, was about a 6. The Chile would have been 10, 100, 1,000, over 1,000 times more powerful than the atom bomb. The Mount St. Helens eruption was a little less powerful at about 7.7. Damage, ground shaking, causes some problems. Liquefaction, this is kind of neat. This is when loose soil acts like a liquid. Um, Sand, for instance, is not tightly packed together. So it's a good example of this. If you've ever played with a sandbox, and you've got various items sitting in your sandbox, and then someone comes along and hits the side of the sandbox. All of the sand is shocked, and so the individual particles are temporarily suspended between each other, and then the entire thing is able to move more freely, like a liquid. When that happens, it'll make smaller objects sink into the sand. Obviously, when we're talking about the planet, the objects could be things like buildings. This is what destroyed a great deal of San Francisco at one point in 1908 when there was a really nasty eruption, nasty earthquake. And much of the soil was actually loose packed soil. And so many buildings sank halfway into the ground, which destroyed them. You get aftershocks that may cause further damage, and tsunamis, of course, you're aware of, started by underwater earthquakes. Here's a tsunami image. You've got an earthquake happening out at sea, and it produces a shock wave. And the shock wave radiates out and then produces a wave. Out at sea, it's not a problem. If you're scuba diving out here, or on a boat out here, you'll float right over it and not even notice the difference. However, when it reaches shore, the tsunami ends up, because it is so large, being forced more and more above the waterline because of the ocean floor pushing it. It will suck the water out to sea temporarily to create this massive wave. As you can see in this general scale, it can be several stories high and cause incredible disruption. The biggest problem with earthquakes, though, is not so much the shaking. If you're out in the middle of a field, the ground shakes, you fall down. Ow. That's the worst damage you're going to get. However, the various items we build can cause problems. Dams can break, causing massive floods. The utilities break, can cause fires. Imagine if you have a fire next to a gas pipeline. This is the most important reason why we need to have great control over our power lines and gas lines. One of their terrors in San Francisco and LA is that a gas line will break during an earthquake and produce an explosion. So they have various different items of places all over that will turn off the gas whenever there is an earthquake. Emergency planning, you drop, cover, and hold. So you drop to the ground, you get under a strong object like a table. The lab desks in science would be excellent for this. And you hold on to the table so that the silly thing doesn't shake right out from it, so you don't shake right out from under it. And the best thing is to be outside. However, running outside while you're inside a building during the earthquake isn't a great idea. You're likely to trip and fall, and things could fall on you. So during the actual earthquake, just get under cover, and then once the earthquake is over, rush outside. Now, finding the distance from the epicenter. What you do is first you look at the arrival time of the P and S waves. So like earlier, we found that the P and the S waves were roughly 30 seconds apart. So we have these graphs of, it's called the SP lag time, meaning the time difference between the S and the P wave arrivals, and distance. Any seismograph has this built in. We've got computers now. So you find 30 seconds, and then you follow it across until you hit this graph. And at 30 seconds, that means you are roughly 291 kilometers away from the epicenter. Kind of neat. If there's so much as a 30-second gap, we are almost 300 kilometers away. And if there's a smaller gap, then we are much closer. If you only had a 5-second gap, for instance, then you'd be 50 kilometers away. What's happening is, if you imagine two runners, a P wave is your fast mover, and the S wave is your slow mover. As they both leave the gate, they're pretty close to each other when that bell rings. But then the longer you go, the bigger a lead the fast one gets over the slow one. So the gap between your fast and your slow moving runners tells you how long you are from their starting point. So locating the epicenter is called triangulating. And if you look at the beginning of it, it's tri, 3. So you need 3 seismographs in different locations to determine the epicenter. That's what's going on in this image. Chicago measured the time lag between the P and S waves and found that the earthquake happened 2,975 kilometers away. So they draw this massive circle around Chicago. It happens to hit the west coast in many different places. So the earthquake must be somewhere along this line, somewhere up in Alaska, Washington, Oregon, California, or could even be out to sea or down in Mexico. And that's a whole lot of places it could be. So you call El Paso. And El Paso says, well, it's 1,600 kilometers away from me. So it's somewhere on this circle. Okay? So it's both on Chicago's circle and on El Paso's circle, which meant that it would probably be in 2 locations, either this place right here in California or somewhere down here. Unfortunately, there's not an overlap of the 2 that you can see. And then Medford measures that it's 500 kilometers away. So it's somewhere on this circle. There's only one place on the globe that's this distance from Medford, this distance from El Paso, and this distance from Chicago. And that's this point right here. And that is the epicenter of the earthquake. There's something else we can determine using the seismograph. Again, here's our seismograph. This time lag gave us how far away it is. But how much it jumps is called the amplitude. And that tells us how powerful the earthquake is. So we have this kind of odd graph over here. The left is showing us distance, and the right is showing us amplitude. Obviously, if we were very close to it and it jumped 11 millimeters, that would be a different thing than being thousands of kilometers away and it still makes us jump 11 millimeters. All right. So we need distance and amplitude to find out our magnitude. And we draw a line, and we were 292 kilometers away, and our amplitude is 11 millimeters. So we draw a line between the 2, and it intersects the Richter magnitude at 5.0, which means that the Richter magnitude is a 5.0 earthquake. If we were closer to it, say down at 40 kilometers away, and it made us jump 11, it'd be intersecting more along here. So it'd be hitting, say, around 3.5 magnitude. If we were 800 kilometers away and 11 millimeters of magnitude, then it would intersect apparently right around 6.5. It'd be a more powerful earthquake because even 800 kilometers away, it made a powerful jump. So that's how you use these seismograms to determine the strength of an earthquake as well as its location. There is one last thing that these earthquakes teach us, and that is about the interior of the Earth. Here we have a cross-section of the Earth, and we're going to let loose an earthquake right here. Radiating out from it will be the P and the S waves, and we're going to see what happens. When I hit play, notice the P wave and the S wave. They left the earthquake at the same moment, but since the P wave moves faster, it is pulling away from the S wave. And then as it goes further, something interesting happened here. There's this yellow bit, and some of the P wave bounced off, and some of it went through. What this indicates, this refraction it's called, this bending of the wave, is because there's a density change between the mantle and the outer core. This is how we learned about the outer core. Kind of neat. And we let it go further, and notice the pale blue, the S wave. It did not enter the outer core. It bounced off. None of it went through. So think of what you know of P and S waves. P waves can travel through anything. S waves only travel through solids. Therefore, the outer core must be a liquid or a gas. Since it's extremely unlikely that a gas could make up the majority, make up such a large layer of the Earth because it is under so much pressure, it must be a liquid. And that makes sense when we learn about the temperature of the Earth inside, that it's above the melting point. So the outer core then must be liquid. And it still goes, and notice the P wave breaks again at this lighter colored part in the center. This is how we learn that we have an inner core, and it has a different density than the outer core. What's also neat is, although the S wave can't get deep inside there, notice that the P wave is able to move faster through the center than it is through the outer core. That's because this area is more dense, which tells us it is probably no longer a liquid, it is probably a solid. So if we let this go, we get these echoes from earthquakes all over the planet. Every earthquake can be detected all over the planet. And we get basically something like a sonogram, a sound picture of what's going on inside the Earth. And this is how we learned about the interior of the Earth. So we've gone full circle from learning about discussing the interior of the Earth, discussing plate tectonics and how the crust parts move, to discussing earthquakes, which gave us further evidence for their interior of the Earth.